In this video, we're going to look at implicit differentiation. Most equations we've seen in the past can be written in the form y is equal to the f of x. An example might be y is equal to 2x squared plus 1, or y is equal to cos x. These give y explicitly as a function of x. So, on the left-hand side, we have y and y only, and on the right-hand side, we have an algebraic or trigonometric expression involving x's and constants, or constants. Often it's not convenient or even possible to write y explicitly as a function of x. So for example, if we had xy plus cos y is equal to e to the x, we would now struggle to make y the subject. In this situation, we believe y is a function of x and say y is implicitly defined as a function of x. What we're going to do is start off with some basic understanding given an equation we know. So let's take an equation we know. Let's go for x squared plus y squared is equal to 1. This is the unit circle, or the equation of a circle, centre 0, 0, radius 1 unit. And we'll just draw a quick sketch of it here. Now, as we can see, this isn't y as a function of x. So let's draw this up, and we'll have something that looks like that. So what I've got then is some point here, and this point will be x comma y. So that's some point now on the circumference of the circle, x comma y. What I could do is look now at making y the subject. Currently, this isn't a function of x. Y is not a function of x. If we just look at this now, this would not pass the vertical line test. We can see here that this value of x gives rise to two different values of y. So this is not currently a function of x. What I could do at this stage is now write this as y squared will be equal to 1 minus x squared. So now I've made y squared the subject. Taking the square root, we're going to have now y will be equal to plus or minus the square root of 1 minus x squared. Still, we don't yet have a function unless we define this as two different functions. We could say that y is equal to the positive root of 1 minus x squared when y is greater than 0, so we're above now the x-axis, and we could say that y is equal to minus the square root of 1 minus x squared when now y is going to be less than 0. So what we could have done is split this up. Now, as you can see, this is quite messy, and we haven't even defined this for when y is actually equal to 0. Let's go back now to this point right here, this point x comma y. If I drew the radius from the centre to that point, we can see now that that has a gradient of y over x. So y over x is the gradient. If I now introduce a tangent, we're going to have now the negative reciprocal as the gradient, as the tangent creates a 90-degree right angle with the radius. So we can believe at this stage now, based on the coordinate geometry we've seen before, that if we have, and let's just make that look a little tidier, if we have now the radius and the tangent, we can say the gradient of the radius, which I'll call mr, will be equal to y over x. Therefore, we can say from here that the gradient of the tangent, which I'll call mt, is going to be minus x over y. Therefore, if I wanted now the gradient of the tangent at any given point on this curve, we could say dy by dx will be equal to minus x over y. Now, this intuitive sort of understanding is going to help us really get to grips with what we're seeing here. So if I now split this into two functions, we can see that we could take y to be greater than 0, which is now going to be above the x-axis, and we could take now y to be less than 0. Let's first take y to be above the x-axis and y be greater than 0. So what I'm going to do is rewrite this. So y is going to be now the root of 1 minus x squared, which I can write as 1 minus x squared to the 1/2 power. So if I wanted to find the derivative dy by dx of a gradient function, I could now differentiate. I've got now a function of a function, so I can use the chain rule. So multiplying down by the power, rewriting the inside function, dropping the power, and multiplying through by the derivative of the inside function, we end up with this expression for now the gradient. So if I just do a bit of tidying up, as it were. What we have, the 2's are going to cancel. We're going to have now minus x over now 1 minus x squared to the power of minus 1/2, which I could write as the root of 1 minus x squared in the denominator. Now we know that y has already been defined now as a positive root of 1 minus x squared, so we can say y is equal to the square root of 1 minus x squared. Therefore, from this point we can say now that the derivative dy by dx would be equal to minus x over y. So as you can see, it holds. We could do exactly the same at this point right here. So we could do this now for the negative root, and we would see we're going to get exactly the same. We're going to get now that dy by dx is minus x over y. So let's just show that that's the case just here. So let's take now y to be less than 0. So we're interested in now this below the x-axis. So if I consider now that y is equal to the negative root of 1 minus x squared, we've got 1 minus x squared to the power of 1/2. So the derivative, the gradient function dy by dx, so I'm differentiating both sides of the equation with respect to x, multiplying down by the power, rewrite the inside function, drop the power by 1 and multiply through by the derivative of the inside function, which is minus 2x. This gives me at this stage now that dy by dx is equal now, the 2's are going to cancel, we're going to have x over the root now of 1 minus x squared. Now if we consider what we've got, that at this stage, considering what we have here, is minus y. So we can say yet again dy by dx is equal to minus x over y. Now we've only considered this now for values of y greater and less than 0. We've not even delved into looking at when y is equal to 0. As you can see, this is problematic, and that is dealing with just x squared plus y squared is equal to 1, which is relatively straightforward. Now, if we were to try this with the example I gave earlier, for example, if it was xy, which is a product, plus cos y is equal to e to the x, you can see that's going to start getting very messy. So what we need is an alternative approach. I think by this stage we're fairly convinced now that we can see geometrically this holds. We can see algebraically it holds for two different functions. Therefore we have to believe that the derivative now, dy by dx, for this particular equation is minus x over y. So at this stage what we're going to do is rely on the understanding that y is defined as a function of x. So let's go ahead now and look again at x squared plus y squared. So x squared plus y squared is equal to 1. Now what I want to do is find the gradient of this equation, dy by dx. What we do here is differentiate both sides of the equation with respect to x. So I get the derivative with respect to x of x squared plus the derivative with respect to x of y squared plus, it's equal to the derivative with respect to x of 1. The derivative with respect to x of a constant is just going to be 0. So let's go ahead, nice and straightforward, x squared, if we differentiate 2x. I'm going to leave this alone right now, and we're going to say the derivative with respect to x of y squared will be equal to 0. So this is where we currently stand. Now what we need to believe here is that y is a function of x. So we can say that y is some function of x. What I'm going to do at this stage is use the chain rule right here, because we have y as a function of x. So if you wanted to look at this now, this is the f of x squared. So we've got a function of a function at this point. Now when we've got a function of a function, we use the chain rule. So what we're going to have is the following. We're going to have 2x plus, now we're going to differentiate the outside function, which is going to give me now multiplying down by the power, rewriting the inside function, dropping the power by 1 and multiplying through by the derivative of the inside function. So the derivative now is going to be dy by dx. If I want to differentiate a function of x, the derivative is dy by dx. And that is going to be equal to 0. So what I've done is employed the chain rule. I've said now that y is a function of x. So what we have is that function of x squared. I've multiplied down by the power, dropped the power by 1, rewritten the inside function now, where y is a function of x, and multiplied through by the derivative of the inside function, which will be dy by dx for whatever function this is of x. So let's go ahead and rewrite this now. We've got 2x plus 2y dy dx is equal to 0. So if I just divide through by 2 and subtract now x from both sides, y dy dx will be equal now to minus x. You can see what's coming from here. I'm going to divide through by y. So we can say dy by dx will be given now to be minus x over y. So this is going to give us exactly the same as what we've looked at before. We've assumed that y is a function of x. It's implicitly defined as a function of x. So what I've got is some function of x squared. I've employed the chain rule and simply rearranged to give dy by dx in terms now of both x and y. So from this point, assuming y to be implicitly defined as a function of x, we can say, and this is a general result, the derivative with respect to x of now f of y is given now equal to the derivative with respect to y of f of y multiplied by dy by dx. Now this looks quite formal. In all honesty, you don't have to really quote this time and time again. We differentiate the function with respect to y and then multiply through by dy by dx. So what we'll do is a few straightforward examples and see how we can differentiate now implicitly defined functions with respect to x. So let's work on a few. Let's just write a few of these out. So what we've got here is x cubed, and we'll have plus 2y squared plus 3 is equal to 0. Okay? So if I differentiate each of these terms with respect to x, differentiating x cubed gives me 3x squared. Now I'm going to differentiate 2y squared. I differentiate with respect to y and multiply through by dy by dx. So if I differentiated this now, I would get now, multiplying down by the power, I get 4y to the power of 1 multiplied by dy by dx. So all I've done is simply employ the rule that I said earlier. Differentiating a constant will give us 0, so we'll have 0. So we can say now that 3x squared plus 4y dy dx is equal to 0. Now at this stage you can of course express dy by dx in terms of x and y. Often you'll be asked to do that. If you're simply evaluating a gradient, so if you're finding a tangent or a normal, then you could just leave it in this form. But if we wanted it now, dy by dx in terms of x and y, we're going to have now minus 3x squared over 4y. So I've got both now y and x in my derivative. Okay, let's look at another one. Let's go for, let's try something slightly more interesting. Let's say the natural log of y plus e to the x is equal now to 4. So what we want is an expression for dy by dx, the gradient function in terms of x and y. So if I differentiate the natural log of y with respect to y, I'll have 1 over y. We now multiply by dy by dx. I differentiate e to the x, I'm going to get e to the x, and I differentiate a constant, I'm going to get 0. So we end up now with dy by dx will be equal to, subtracting e to the x from both sides and multiplying by y, we'll have minus y e to the x. So all I've done now is express dy by dx in terms now of y and x. Let's look at something else. Let's say we've got, let's go for xy. So let's say xy minus y squared will be equal to, let's say, some constant, let's say 14. We have a product here. So what we need to do is use the product rule. So let's go ahead and do that. So what we've got then, we will have now u, we're differentiating this with respect to x. We will let u be equal to x. We will have the derivative du by dx with respect to x will be 1. If we take our v term to be now y, the derivative dv by dx will be now dy by dx. Remember, this essentially is y to the first power. So what we've got now is the derivative dy by dx. The product rule says we multiply v by du dx and add to it the multiple of u dv dx. So we end up now with y, and then that's just going to be y multiplied by 1, which I'll write as y, plus x dy dx. We now need to differentiate minus y squared with respect to x. So we're going to get minus 2y, that's differentiating now minus y squared, dy dx, and that will be equal to the derivative with respect to x of a constant, which will be 0. So at this stage now I can make dy by dx the subject, and I can say that y will be equal to dy by dx, and I'm going to have 2y minus x. So 2y minus x, and if I wanted to write dy by dx in terms of x and y, I could write this as now y over 2y minus x is equal to dy by dx. So I now have my derivative dy by dx in terms of x and y. So exactly the same as we've done before, but when we have a term involving y, we simply differentiate with respect to y and multiply through by the derivative dy by dx. Let's do another one. Let's have a go at another one. Let's see what else we can do. Let's say we've got now sine of x plus y is equal now to 4x. So what I've got now is a function of a function here. So we've got functions inside a function as well. So let's differentiate the outside function. So we can have cos of x plus y. We now need to multiply through by the derivative of the inside function. So I've differentiated the outside function. So if this was sine of u, it becomes cos of u. We now need to multiply through by the derivative of the inside function. The derivative of x is 1. The derivative of y is now dy by dx. So we have now 1 plus dy by dx, and then that will be equal at this stage now to 4. So I could write it like so. I could go ahead and make dy by dx for subject if I liked, but that is essentially what we're going to get. We differentiate the outside function and then multiply through by the derivative of the inside function. The derivative of x plus y with respect to x is 1 plus dy dx. When we differentiate x, we get 1. When we differentiate y with respect to x, we get dy by dx. Okay, so there we go. Nice straightforward work. What we're now going to do is look at finding a tangent. In later videos, we'll do a lot more work with these. The idea of this video was to give you some understanding of how this works and how we can apply it. But we may as well look at finding a tangent before we go. So let's find the tangent now. Let's say we want a tangent for some implicitly defined equation. Let's say we've got now an equation, and let's make this quite tricky. Let's say x multiplied by the natural log of y plus, say, y multiplied by the natural log of x is equal to 1, and we want now the equation of a tangent, and we'll have a point now 1 comma e. So what we've got here is a product, and we've got a product. So I'm going to need to use the product rule on each of these parts. So what we've got is the following. We've got now, on the first one, we'll have x and its derivative. So we'll have x and 1. We will then have the natural log of y. Its derivative with respect to x is its derivative with respect to y multiplied by dy by dx. So what do we end up with then? We can say that we're going to have now the natural log of y multiplied by 1. So that is v multiplied by du dx plus u multiplied by dv dx. So we're going to get the natural log of y, then we will get plus x over y dy dx. So all I'm doing is simply employing now the product rule. So x over y dy dx. Let's now consider the derivative of y, the natural log of x. So what we'll have is the following. We'll have y and its derivative with respect to x. So y, its derivative will be dy by dx. Again, if this was y squared, 2y dy dx. If it was y cubed, 3y squared dy dx. If it was cos y, it would be now minus sine y dy dx. Natural log of x, its derivative with respect to x is 1 over x. So what we've got here is plus now the natural log of x multiplied by dy dx plus now the y over x. So plus y over x. And now all we need to do is differentiate the constant. Differentiating the constant is going to give us 0. If you like to think about that, what is the gradient now of the straight line 1? Well, it's 0. So there we go. Okay, at this stage now, we want the function here. We should say we want the gradient function. Now, I could express dy by dx in terms of x and y. Unless I'm asked to, I can simply evaluate it now at the point here where x is 1 and y is e. Now, often before, we just had a case of finding dy by dx when x was something. But now, of course, we've got now these expressions that involve both x and y. So we're going to sub these in. So for the tangent, I need now a point that it goes through, which is just there. And we need m, the gradient. Once I've got those, it's going to be a straight line. So what we're going to have then is the natural log of e. So what I'm going to do is just write these in and then we'll just evaluate. The natural log of e plus now x over y, which is 1 over e dy dx. So dy dx plus the natural log now of 1. The natural log of 1 is 0, but we'll put this in anyway. So the natural log of 1 dy by dx plus now y of x, which is just going to be e over 1. And that's equal to 0. The natural log of e is going to give us 1. This is basically saying log base e of e. What power is e raised by to get e? The answer is 1. Plus now 1 over e dy dx. And then we're going to have this one right here. Now the natural log of 1 is 0. So all of this now term is going to be 0 plus e is equal to 0. So at this stage now, I can make dy by dx the subject on this and simply go ahead and find the gradient. So I'm going to have now, just rearranging, 1 over e dy by dx will be equal to minus the quantity e plus 1. So from here we can say now that dy by dx, so let's do this, dy by dx will be equal to minus e. Remember, e is just a constant, it's 2.718 and so on and so forth, e plus 1. Or if you like, you could save it dy by dx. If you really wish, I prefer to take the common factor out. You could say that this was minus the quantity e squared plus e. I prefer the first one, but it doesn't really matter. So we want an equation for the tangent to this curve at the given point. So we've got now our gradient, and our gradient is minus e multiplied, let's just put this here, minus e multiplied by e plus 1. Okay, so let's go ahead and just sub this in. Straight line equation, y minus y1 is equal to m the gradient, x minus x1. So I'm just going to sub this in. Use y is equal to mx plus c if you like. So what we're going to have then is y minus e will be equal to the gradient, which is minus e, the quantity e plus 1, multiplied now by x minus 1. So that's what we have, and I'm going to leave it in that form. I'm not asked to put it in any particular form. I've not put that condition on myself to have it as y is equal to mx plus c. So this now is an equation for the tangent at the point 1, e. All we've done is use implicit differentiation. Whenever we've seen a term in y, we've differentiated with respect to y and multiplied through by dy dx. So we end up with this expression. If you want to go ahead and tidy that up, you can do, but that is an equation. Remember, an means any form. The equation generally means that it either be in the form y is equal to mx plus c or ax plus by plus c is equal to 0. So an equation, just leave it as is, as it looks a complete mess. So there we go, an introduction to implicit differentiation, and in later videos we'll work through a range of different examples involving derivatives.